Hello everyone. Today we're going to talk about fields and forces part 2. Well, fields and forces are two words that pretty much explains every reaction, every physical and chemical event throughout the cosmos. It's like as if we live in a sea of waves and oscillations and cycles and loops and fields and forces, right? If you have a field in the presence of particles, this field can lead to forces. There are two that we focus on in physics, which is electromagnetism and gravity. The force of gravity between two objects is negative gmm over r squared. The negative means the force is always attractive. We haven't found anti-gravity yet, so gravity is always the force of gravity is always negative. The electric force is kqqq over r squared. K, the Coulomb's constant, and G in the gravitational force equation is gravitational constant. These are constants of proportionality. The m's in the gravitational force are the masses, and the q's in the electric force are the charges of the objects. The electric force is negative when the force is attractive and positive when the force is repulsive. Now, if you have a single particle with mass, in the absence of another particle, there is a field coming from that particle with mass, the gravitational field. The gravitational field on Earth is 9.81 meters per second square, is the gravity on Earth. There's also electric fields from single particles, from single charges. We also have something called potential energy, which is the potential to be converted into kinetic. The potential energy for gravity is negative gm over r, only one r at the bottom. And for the electric field, the potential energy is kqqq over r. The potential, like we've talked about in the past in other videos, it's the potential which is energy stored, which means that when released, that energy is converted into energy of motion, kinetic energy. And you also have something called potential. If in the absence of another particle, in the absence of another star or massive object, there's still a potential will from that point source, from that charge, from that massive object. And then for gravity is negative gm over r, and for the electric field, the potential is kq over r. It's the potential due to that one particle. And of course, the arrows here represents that you can convert from one to the other. For example, the derivative of potential over distance gives you the field, such as gravity. The derivative, if you have a graph of potential over distance, um, the derivative of potential with respect to the distance will give you the gravitational field or the electric field. The units for potential energy are joules, and the units for potential are joules per coulomb or joules per kilogram. Now, the derivative of the electric potential energy will give you the force for the electric force, and also the derivative of gravitational potential energy with respect to distance will give you the gravitational force. So here's an example how you can move from potential to field and potential energy to force. force is measured in newtons, and fields are newtons per coulomb if it's electromagnetism, or newtons per kilogram if it's gravity. The slope of a graph of potential energy over distance is force. The slope of a graph of potential over distance is field. It's what we were talking about it before, that the slope would be the derivative with respect to the distance. Gravitational potential times mass will give you gravitational potential energy, because the only thing missing is the other mass. The electric potential times a charge equals the electric potential energy. You can only have energy if you have more than one thing in space and time. If you don't have anything in that space and time except for one point source of mass, one point source of light or charge, then you have fields and potential. But as when you have a setup with several masses or several charges, then you have energy and forces that play an effect. Force times distance equals gravitational or electric potential energy. Um, and gravitational field times mass gives you the gravitational force. All I'm doing is showing you explaining how you can convert from potential to potential energy to force, from force to field, and so forth. An electric field times charge gives you the electric force. Now, a gravitational electric potential inside a shell can be a sphere that is hollow inside, only has a surface. The gravitational electric potential inside a shell is constant and is equal to the one on the surface. So whatever is the electric or the gravitational potential at the surface of a planet or at the surface of a particle or a object with charge, that potential is the same in its inside. And then, of course, as you move away from the surface out into space, it drops. It follows an inverse relationship where it drops like expected. Gravitational electric field inside a shell is zero. So if you have a shell, a sphere that is hollow inside, both the gravitational and electric field inside the shell is zero. Outside of the shell, the gravitational and electric field drops in the inverse relationship as shown in the image. These are hints and tips to know and memorize, not necessarily memorize, but also understand, because there are proofs for all of this, and this has been experimentally proven to be true. Gravitational and electric field inside a solid sphere increases linearly until reaching the value at the surface and dropping inversely. So if you no longer have a solid sphere, if you no longer have a shell that is hollow inside, but rather you have a solid sphere, then things are a little different. The gravitational electric field inside the sphere drops as you go towards the center, and in the middle of the sphere, it's zero. But then as you move out of the center of the sphere, it rises in a direct proportionality, in a direct proportionality. And then once it reaches the surface, as you go into space, it drops following an inverse relationship. Potential energy increases when moving an object towards a higher positive potential, and potential decreases when moving towards a lower negative potential. Yeah, because you're moving the object to shells, to wheels. So potential increases if you move towards a higher positive potential, and if you move the object to a negative potential, the potential will decrease. Yeah. Potential energy at a location is the amount of work done in moving an object from infinity to that location. That's the definition of what potential energy is. Energy work is also measured in joules. So the amount of work needed to bring an object all the way from infinity to that location in space is the potential energy of the object at that location. Potential at infinity is zero because it follows an inverse relationship. When r goes into infinity, the number approaches zero. Gravitational potential and gravitational force is always negative. They're both always negative. Electric potential and electric force can be positive or negative. And the reason why is because the electric force can attract or repel, but the gravitational force is always attractive. The graph above shows the electric field from two positive charges. Notice that the field is zero at the middle between them. Why is that? Because when you have two charged objects, the field in the middle will be zero because um, the electric fields from both of the particles will cancel each other out. On the graph on the left, where the slope is zero, the gravitational field is zero. Yes, if you have, for example, in this case, the graph above shows the gravitational potential of Earth on the left and Moon on the right. The Earth has more mass, so the graph spikes more than the Moon because the Earth has a bigger potential well. Okay, the Moon has a smaller radius and thus the graph peaks thinner than the Earth. So notice that the electric potential inside an object is inside we normally in this graph, as you can see, we go all the way to the radius of Earth and all the way to the radius of the Moon, and the electric field is zero at a location closer to the Moon than to the Earth because Earth has more mass. So in order for the electric field to be zero or the gravitational field to be zero between the two objects, the point where that net electric field is zero or potential or whatever is going to be closer to the moon because the moon has less gravity than the earth, and this means that and this can also be shown with the slope of the graph. On the graph on the left, where the slope is zero, the gravitational field is zero because the slope of a potential versus distance graph gives you the field. And now for some equations, proof for electric field inside a solid sphere. As we saw earlier, that the field increases linearly inside a solid sphere. It's zero in the middle and then increases linearly all the way to the radius and then it drops inversely. So basically, the electric field times area equals enclosed charge or enclosed mass over the constant of proportionality, which is different for the electric field as it is for gravity. In this case, E naught is the permittivity of free space. We're using an example where the solid sphere is a charged sphere. Now, charge density times volume will give you the enclosed charge at a given distance from the center of the sphere, but it's still inside the solid sphere. So E times 4 pi r squared. 4 pi r squared uh, is the surface area of around a location in the sphere, it's inside, is equal to charge density times the volume, 4/3 pi r cubed, divided by the constant of proportionality. So all we're doing is using the equation that we had at the top, where the electric field times area equals enclosed charge over the constant proportionality. In order for to know the enclosed charge, you got to take the charge density, which is charge per volume, multiply times volume, enclosed, and that you get the charge. And then if you simplify things a little bit, you get the charge density, you get that the electric field is equal to charge density times 4/3 pi r cubed over 4 pi r squared times the constant of proportionality. And this means that if you do the simplification, you get that the electric field is equal to charge density times R over 3 E naught for the electric field. As you can see, there's a linear relationship because the R is not at the bottom, but it's at the top, and it's not square, so the graph will not look like a curve, but will rather look like a straight line. The equation underlined is linear, and thus the field increases with distance from the center and reaching a peak at the surface of the solid sphere. The field is zero at the center where R equals 0, like I said before. So this video summarizes electric fields and forces and potentials and potential energies and how they all relate to each other. Thanks for watching.